Thank you, everyone. It's so great to see so many people here, and I'm excited to talk about a topic that's near and dear to my heart, which is data and how we can use it to transform natural hazards and disaster research. Before I get started, of course, I need to acknowledge those people who influenced some of the comments that I'll make today. We developed a data working group, and I talked to all these folks. We had some great conversations. You'll see I've collected some data and examples from them, so I want to acknowledge them, as well as my DesignSafe team, who I love working with. Most of my co-PIs are here, and of course, the work we do with the Texas Advanced Computing Center. So I want you to think about what might have happened, or what did happen in Southern California at 4:30 a.m. on January 17th, 1994. I'll give you a second to think. You might kind of know from John's talk. But it was the Northridge earthquake. And I have a fun anecdote about this event. I was a first-year graduate student at UC Berkeley. I had just moved to the West Coast for the first time. Obviously, I was in Northern California. This happened in Southern California. But my grandmother didn't know that. She was in New York, and she knew her granddaughter was in California. And she saw the news. She watched the Today Show. And she knew there was an earthquake in California. Fortunately, she waited till 6:30 in the morning, California time, to call me and ask about this earthquake. But think about what we knew in the minutes after that event. Almost nothing, and the things we did know came from the TV. That's it. It probably took us weeks before we could figure out how many people had perished, the injuries, and I'm sure it was many months before we figured out how much the economic losses were. So let's fast forward about 25 years to Anchorage, Alaska, 8:30 a.m., November 30th, 2018. Another event very similar, the Anchorage earthquake, magnitude 7.1. And yes, you would know where it's located. But for this event, and today when an earthquake happens, I know what I do. I go to the USGS. And there is so much technical information available within minutes and then hours, and it evolves over time. But almost immediately, you know the area affected, you know the magnitude. You have estimates of the ground shaking. You have people reporting what they felt through Did You Feel It? You have estimates of ground failure. You have estimates of economic losses. And just to show you at detail some of the things that we look at in terms of the interactive map that is available. And then PAGER, which stands for the Prompt Assessment of Global Earthquake Response. We really have a lot of information at our fingertips. So again, for this event, within minutes, there was a map that showed the ground shaking. And as the day evolved, the ground shaking incorporated felt reports as well as sensor data to estimate that. There were the regions that they have estimated where liquefaction had occurred in the area. And then it's really amazing what PAGER, really how it changes our idea of, do we really need to worry about this event? Very quickly, we realized in terms of fatalities, this event was green. Probably very few. But from an economic perspective, the losses were going to be significant. Not in the red zone, in the orange zone. But it gives us an idea of how impactful this event was. And in fact, if you scroll down, it will tell you which cities were most impacted as well. So, how did we get from there to here? And I stole this from Dave Wald, his Joyner lecture earlier this year. You know, if we think in the early 90s, all we knew was location. And then we evolved to know what the ground shaking levels were, you know, in the early 2000s. So we got a quick shake map. Still didn't really know the impacts. Then later in that decade, we were actually pushing data for ShakeCast. And then PAGER came on to the field in 2011 to 2017. And now today we're looking at ground failure effects as well. But how did we get from there to here? And it really is data-driven models and multidisciplinary collaborations that allow us to make that move. And really networking that all together. So the seismologists needed to understand ground shaking, talk to the engineers about how that may cause damage and what was needed to estimate damage. We need to talk to social scientists to better understand economic losses, what causes fatalities, etc. And although I don't think we do a good enough job with that now, but we need to take that to the next level and think about recovery. How after this event can the social scientists and engineers better understand recovery? And as we heard earlier today, let's also think about before the event, mitigation and adaptation. But the key is the network and the data-driven models, and data is at the key. And that's where I like to think about NHERI. NHERI has a broad array of resources available to support research. The way I like to think about our network is we're a circle. The network coordinating office encompasses us all, but we all work together in the middle. We've got experimental facilities generating data on very specific experimental setups. We've got Converge and the Rapid Center going out to the field to understand the societal impacts and also collect data from these real events. And then in the digital space, we have DesignSafe, where we've got a data repository, cloud-based tools to analyze that data. And the Sim Center has additional computational tools that take advantage of lots of resources, AI, machine learning, so we can better understand impacts. But they're all networked together, data producers, data analysts, so that we make an impact. So just a few examples of what type of data are we collecting. And this I obtained from David Rouge from Auburn University. Often you saw already a lot of examples of hurricane reconnaissance, where, for instance, in Hurricane Harvey here, we can go house by house and look at the damage state. And often, as we've seen so many times, that one house is completely collapsed next to another house that is not. And understanding why is one of the big questions. And it may be the year that it was built, it may be a slight design detail. But understanding that from one example often is not going to explain all the damage across an area. And that's why it's so critical to collect as much data across as many events as possible. And so you can see here as an example some of the work that the STEER network is doing just over a two to 3 year period in terms of collecting data about hurricane damage. Hundreds and thousands of performance assessments, individual buildings. They're bringing in new technologies such that the Rapid Center provides us, UAVs, LiDAR, and even more recently using the idea of street view, so street level panoramas. 400 or 200 kilometers worth of street view data that is now at our fingertips to analyze to get a broader idea of the damage. And when you collect these data, there's a lot of data. And we should not only be thinking about what we can do with it today, but we should also consider what someone might do with it 10 years from now, 5 years from now. We might not realize what they might want to do with it, but to make it available so that they can do it is really a key part of what we're doing. Now, in the geotechnical world, I would argue one of the most important events that have happened in the last 15 years or so were the Canterbury earthquake sequence in Christchurch that caused massive liquefaction across the entire city. There are large segments of the city that are still not, they will not allow them to rebuild because of the liquefaction hazard. Due to, whether you're damaging a house, as the cracking shown here, you lose all your utilities. But one thing that they did in Christchurch, amazingly, is they went and they understood that the damage was so influenced by the subsurface that they went and collected tens of thousands of cone penetration test profiles to profile the soil to understand how the differences in soil impacted the observed liquefaction. Now, I can't take credit with that, and NHERI can't take credit for that, but a lot of that data has influenced liquefaction and is finding its way into published data sets in DesignSafe. So for instance, Brett Maurer at the University of Washington used a lot of that data to develop a liquefaction severity prediction based on the CPT data. And I'll tell you, it's humbling. When you try and analyze 15,000 data points, you're not going to get them all right, okay? It's a bit humbling, but when you see the trends and being able to predict the damage trends spatially, it is quite rewarding. And what I'm really excited to say that Brett has done, so the Christchurch data is available publicly on the it's now called the New Zealand Geotechnical Database, but it's kind of in a raw format. Brett did a lot of work to put it in a format that he could use it for his purpose. Well, he has then gone and published that analyzed data set in DesignSafe that others can ultimately reuse. And we've done something similar looking at lateral spreading, where we developed predictive, we developed estimates of horizontal displacement from satellite imagery, integrated it with subsurface data from the geotechnical database. We published it all in DesignSafe. We're not only publishing the data, however, we're publishing the script that did the machine learning analysis, the training to develop the model. So if you're interested in machine learning and want to see the innards of a code that did that analysis, there it is. And if you want to use that model, we've got another script that actually runs the model on your data. So sharing not only the data, but the scripts and the analysis means someone else can reproduce what you did, build off it, and accelerate the research that we're doing. I think one place that we haven't done as a good job over the years, at least as engineers, is understanding the human dimensions of these events. But we've seen it highlighted already this morning. And I have to thank Lori Peak for providing. Oh, I lost the picture. Can you go back one slide, please? Okay, there is supposed to be a picture in the middle. It's not just Jolie. So understanding the human dimensions of these events is important. So one example is a lot of science has been dedicated towards earthquake early warning. But are the people ready for earthquake early warning? And are our most vulnerable people ready? Those in the schools. So Lori and her colleagues at the University of Colorado went, and again, goes back to the Anchorage earthquake, went up to interview schools to understand their readiness, their willingness, and their ability to incorporate earthquake early warning into the schools. And the reason I'm really disappointed the picture's not there is because the data that they were collecting, they were uploading to DesignSafe in real time within the anticipation of publishing the survey instruments, publishing the data, et cetera. Now, when you talk about social science data, some new things come into play. We've got personal identifiable information. We've got IRBs we have to deal with. But that shouldn't dissuade us from still trying to make that data publicly available so others can use it, because that's the way we can best understand the societal impacts for these events. And that leads to the concept of democratizing science through cyber infrastructure, which is highlighted here in an article by Manish Parashwar from the NSF, who runs the Office of Advanced Cyber Infrastructure. Now, the national academies, as well as others, have recently emphasized the role of data and computation in 21st century science. And NSF's position is that transformative research requires the broad availability and innovative use of cyber infrastructure. Agile cyber infrastructure, integrated, robust, trustworthy, and sustainable cyber infrastructure over time. Problem is, you can't think of it as if you build it, they will come. We can build a cyber infrastructure, but we need to make sure that there is broad access, that we lower the barrier to using cyber infrastructure. We want to have user-friendly portals, training. So when we think about using cyber infrastructure, we have to reach our researchers and our audience where they sit and bring them along to use these advanced tools. Now, I want to mention something you probably should have learned in kindergarten, or maybe before kindergarten, right? Sharing is caring, and these cute puppies really illustrate that. But I want to emphasize that sharing data is also caring. And perhaps for many years you've tried to share data or thought about sharing data. You might have done it like this. This is a shared box drive of mine at the University of Texas. You might be able to navigate that. You might not if you're not a geotech. Most people, how many of us have emailed a former student and said, can you get on that box? What's in this folder? My new student doesn't know what's going on. We're trying to use these data. So the key is, yes, sharing data is caring, but sharing organized data is really caring, okay? And we really need to organize the data in a way that others can reuse it without having to email you, call you, text you to understand what's going on. And that's what we try to do in the DesignSafe Data Depot. When you look at a published data set in DesignSafe, there's a clear title, authors, there's an abstract, so like a paper. And as you scroll down, we use color to help you organize how the data are represented. Now, I still remember Bruce Cutter back in the day saying to me, I want tools, not rules, right? So yes, organize, but don't tell me exactly how to do it, because the fact is a centrifuge test is different than a wind tunnel test, which is different than a field reconnaissance test, definitely different than social science data, right? So we provide you the flexibility to organize it, but within a pretty broad framework. And of course, we want you to get credit, so you can see we have DOIs, digital object identifiers, which I'll mention at the end. So now it's the third talk of the second session, and we're going to hear about wood again. And John didn't pay us, I'm sure. But I thought it was interesting when I heard John was going to talk. I said, let's see what data is in DesignSafe, okay? And going back to the NEIS data, because remembering that the NEIS data is in DesignSafe, and you just do a quick search on wood, and in fact, the e-defense tests come up, several other tests come up, and so that data remains available. And if you go to the NHERI part of the data depot, we see that the tall wood, or at least the tests from 2019, the two-story that John showed are there. And I know they're working on they're thinking through early on how to get the data from the tall wood test into DesignSafe 2. So it will be there. But what I was really excited, and I just found out this example recently, is how the data are being reused is really very inspiring. So Eric Hernandez, I do not know Eric Hernandez if he's here. Hi. He is an associate professor at the University of Vermont. And in 2014, he got a career award on structural health monitoring on minimally instrumented buildings. He had an idea. He developed the framework. You see the framework here. You've got some acceleration measurements. You've got a nonlinear model of the system. You've got some estimations in the end, and you're trying to come up with a performance assessment. But it's still just an idea, and of course you test it, but you probably test it on theoretical data, not real experimental data. But that's where Eric worked with John and the rest of the Wood group to use the data from the e-defense shaking table test to test the methodology, and you can see that work was published in 2019. So I'd argue this accelerates the potential adoption of that work because the data were available. He didn't have to write another proposal to do a big experiment to test his theory. He had the data available at his fingertips and could accelerate and do that very quickly. The last example here actually comes just from this August. And in fact, it comes from a New York Times cover story from August 12th, the coming California megastorm. For years, we've talked about the big one in California, and it always meant an earthquake. But these climate scientists are arguing that a different big one is coming, and it's these large storms, megastorms, that can cause significant damage. Maria Esteva, our data curator, saw this in the New York Times and kind of linked it back to a science article. Not surprising, New York Times will often highlight something written in science. So climate change is increasing the risk of a California megaflood, researchers at UCLA. And then we dug a little deeper into the citations and the references for that paper, and it points to a data set in DesignSafe. It's a data set from ArcStorm 2.0, so these are atmospheric simulations of rainfall across the entire state of California. And they had the forethought to think others may want to use this. Those who study landslides, flooding, under these new hazard scenarios now have the data at their fingertips, I'll say it again, at their fingertips, so that they can then look at what the impact of these megafloods would be in the future. So the last thing I want to point out is data counts. I think we all should think of data and publishing data and reusing data as scholarly endeavors. So I've gotten to the point where every one of my graduate students, when they publish a paper, they publish a DesignSafe data set. That's not just the data, but the scripts, the analyses that go along with it. Because I know that will accelerate adoption and accelerate someone else being able to use that research. Data counts means you need to publish things in a formal data repository with a digital object identifier. It means when you use someone else's data, give them credit. Not in the acknowledgments, not in the abstract, in the reference list with the data cited like a paper with a DOI. It is a scholarly effort that they publish the data and shared it with you. Give them credit through citations in a proper way. And all of that goes towards our hope that we extend the data life cycle. This used to be what the data life cycle was. I generated some data, I analyzed it, I published a paper, I was done, I moved on. I hope now that we all will publish both the data and the paper. And then if those data, as those data are around, perhaps we can integrate data from other sources. If we think about harnessing AI and machine learning, you're going to need more data than any one person can generate. You're going to need to pull data from different sources. So here, we've got that data available. Maybe you bring in some new data to fill a gap in the existing data. You analyze that data together. It's not done there. Publish your paper, but publish the processed data, the aggregated data, so someone can build off that data set as well. And if that is the case, then I hope that we really will be an interconnected research community that is harnessing our data, our computation towards reducing the impacts of future natural hazards. Thank you.